Recording is rolling. It is Wednesday, August 13th. So I want to take a day, as it's going to be today, to throw a bunch of physics questions out at you guys that you guys are going to see over the course of this year. And just get you guys thinking on some of these. I want to try not to answer these as much as I can, but just get you guys thinking. All right. Found a couple questions from each section and something's not even on the AP exam. So get some of those too. Yeah, I was hoping to have some extra time so I could do some of these other things, but this is going to take most of the class, which is all right. So see if I can maybe fit in some of these other things another day too. What else here? Ooh, I'll tell you guys how this week is going to finish out. Is this right here? I'm gonna have you guys construct this Geneva drive. Yeah, so you guys get to work with each other, work with your friends, work with your hands, think in 3D. Right. So if I pull this apart, pull this apart here. Boink. Right, you guys see some Maxwell systems here. Right, get you guys thinking how this might work. Right. And if I put this together, I bet I want to put this one on first because it's got these pegs that are extending upward. Right, and this tooth gear here. Watch what happens as I hand crank this one on the right. Hand crank this one on the right. You guys see the one on the left turns incrementally because these pegs are catching these teeth. You guys see that? Ooh. Now, where do you think you might have seen or heard one of these? Where would one of these be useful for? Geneva Drive. Huh? A clock. Aha. Tick tock. Ah, a clock. Right. It's called a Geneva Drive. Hey, Geneva, that's a town in where?
Switzerland.
Switzerland, which is known for making clocks. Aha, clocks. Tick tock. Could you imagine if it's like the year 1500 and all you've ever seen, you've just been working on a farm, like milking cows and stuff, and somebody shows up with the hand crank pocket watch, pulls that out. Like, whoa, I can keep climbing down. That's like magic, right? You know where else this one shows up? Suppose you take a time trip to about 100 years ago. Those old movie projectors going. But how do you guys think you turn a roll of film into like let's call it like 30 continuous or incremental frames per second? You throw one of these in there. Yeah. Little clicky clack. It's one of these. Right. Yeah. So that'll be adventure for the next couple days. I always like to have a project like this near the beginning of school, so you can definitely do something to good with the class time, show up at school, and exercise these different spatial skills. Yeah, I'm waiting for schedules to settle down a little bit, and there's a bunch of students swapping classes and that sort of thing. Yeah, we do that. Yeah, in the next couple days. So look for that. Oh, one more thing before I switch over to my presentation is show of hands. How many guys have a planner by now? Who has a planner by now? All right. See, a bunch of guys have a planner. Right, guys, if you have a planner, use it. And hopefully you are starting to use it. If not, then start using it today. If you don't have a planner, then I do want you guys to go home and ask your parents to get you a planner. You can start using that. Right. So, any questions so far? You guys all right? All right. And there is a little bit of paper out on those bar stools. You guys can use that as a temporary planner if you need it. All right, so yeah, let's pick up here. Now, this is a little bit outdated for a number of reasons. It's from 2018, so it goes back a few years. But these are AP scores by subject. You guys see this? So, so dark green is how many students got a 5, which is the highest score you can get. You need at least a 3 to pass. That's this yellow band. And then these pink and the red are 1s and 2s. So those are students who failed. Okay? We got all these subjects here, all these subjects. And oh, what's this one at the top? Physics 1, algebra. Hey, that's the one you're in right now. It's the hardest exam. Now, truth be told, this is a little bit outdated. AP has changed the exam a couple of ways since 2018. And during the pandemic, when underwent some changes. Last year, they reformatted it again, and the pass rate went way up for everybody. So traditionally, this class only about 40 to 45% of students ever passed. But last year it went up to like the 60s. In fact, that's exactly what it was for the class last year. So to rewind the clock, just a few months ago, there was a different set of students sitting here, maybe some of your friends who are seniors now, who were sitting in this class, and this is exactly how they did. So I had one AP Physics last year, and this is exactly how they did. I had 4 students get a score of 5. 3 and above is passing, and 61% passed. Right. So all else equal, that's kind of what you're looking at. I really do think because seeing these students all year, like right now, you guys all look the same to me. it's like everybody's sitting here and listening, which is good. I do have a good feeling about you guys after just a couple of days. But as the months roll by, you can kind of tell who like loses interest or doesn't try as hard or whatnot. But I think if you are engaged in the class, you do everything I tell you guys to do, and you're on top of all your studies, you will pass this exam. It's pretty tough. 61% last year, but yeah, you're pretty good. So FYI, that's what it looks like. All right. Oh yeah, calculator you're allowed to use in this class. I think I mentioned this before, but just to make sure you guys know. What are you allowed to use? So pretty much anything that does not connect to the internet. If it connects to the internet, then don't bring that to the AP exam because that'll disqualify you, right? I have these little TI-30X2S scientific calculators, buy for like $10. Right? Guys, what if you have a TI-89 titanium star graphing calculator? Are you allowed to use that on the AP exam? Yeah, turns out you are. So if you have a really fancy graphing calculator, it's like $100, then yeah, as long as it does not connect to the internet, good to go. If you know how to use it. Okay. All right. All right, set these questions. So how can you measure and quantify your observations? Right. So and think about this too as from maybe near the end of the class, have some time. How do you guys think about how did we even get to this point where we're all sitting in the classroom here and trying to learn from a PowerPoint, right? What was like say 100,000 years ago? We're all running around the savannah and maybe like counting giraffes or something. Right? At some point, realized to do agriculture, we need to count more sophisticated things, get higher numbers, and we start to wonder like, hey, what things are out there to even measure, and how can I quantify them, right? And so maybe the first written directions you see from thousands of years ago, people say, okay, well, if you want to build this table, it's going to be like 20 palm widths wide. It's okay, 20 palm widths, but what's the width of a palm? And that changed person to person. And then maybe every locality had its own sort of standardized units. But then it'd be really nice to be able to pick up a scientific paper from, say, like Japan and be able to follow that. Okay, yeah, they're working exactly these units of measurement. We know exactly like what is the speed of light down to the nearest meter per second, right? Okay. Yeah, and what things are out there to even measure? Like how many things can you like even measure, and how are units related to each other? So if I push or I pull on something, I'm going to call it a force. So a force is just a push or a pull. Okay? It turns out that the units for force are related to things like mass and distance and time. It's all embedded in there. You need to know mass and distance and time before you can know how to push and pull on things. You're paddling across a river. The river is flowing downstream. How can you determine your speed and direction relative to the shore? Now, in this class, those two things right there, speed and also direction, we're going to call that velocity. And when I say velocity, that means both speed and direction. Sometimes direction is implied, or going forward or something. Right? But hey, what if you had a river that was flowing like west to east, and you're trying to paddle from south to north, right? And there's some monkey sitting in a tree, and it's watching you in your boat. Say, okay, well, you're trying to paddle that way, and the river's going like perpendicular to that, right? And the monkey points a radar gun at you. Again, the monkey's at rest relative to the surrounding land, right? How fast, what direction, little protractor. If you know the speed of a car and the distance to the next town, can you calculate the time to reach your destination? Actually, this one you guys can probably do right now. Let's do one of these. So you're on I-95, you're driving north. You see a sign that says Jacksonville is 140 miles away. Okay, about 140 miles. You're driving 70 miles per hour.
2 hours.
2 hours. There you go. Okay, so that one you guys can do. 2 hours, right? Okay. What about these equations? But what if you're speeding up in the car? What if you're slowing down? How can you quantify that? What would that feel like? Right? Vectors. What if you got a plane that's flying through the air at however fast? You guys think the instruments on the plane are probably reading how fast is that plane's engine's really pushing against the surrounding air? Right? Now, if the whole air mass is not moving, let's say there's no wind, then wouldn't that also represent the plane going against the ground? Right? So the plane pushing against the air, the plane against the ground. In that case, it would be all the same thing, right? So there's somebody on the ground. They point a radar gun up at the plane and it reads the speed of the plane relative to the ground, right? Now, what if there is wind? And what if the wind's giving the plane a boost, right? So this white vector, I'll call the plane relative to the surrounding air. Maybe this light green, I'll call the air relative to the ground. Is that going to make the plane do something relative to the ground? That be this dark green one right here, called a resultant, something like that. Okay. What if there's a headwind and the wind? Well, the plane's fighting the wind, right? Had a headwind, got a tailwind, right? Right. is that going to slow down the plane relative to the ground? Okay. What if the plane's trying to go 100 miles an hour north and there's a wind going 100 miles an hour straight south? Plane just be hovering there relative to the ground? Huh. Right? What if there's a crosswind? Huh. What does that look like relative to the ground? And if you point a radar gun up at the plane, what does that number read? Huh. Of course, I have to give you some numbers. Okay. Right. So on the thumbnail notes I gave you guys a few days ago. Now, these are actually from last year. I just pasted in from last year. So this might be updated a little bit. This might not look 100% the same. But all the silver banners are how to basically measure things, how to quantify things. Right. So it's a bunch of there. Well, of course, there should be getting to this stuff, but take you guys through a little tour of some stuff you have. Right. Right. Now, kinematic motion is the first main official topic by AP's book. And this could be linear motion, so motion in a straight line. Right? And we're talking about driving to Jacksonville, but hey, what if you speed up or slow down? What does that feel like, right? How about this? Can you feel the speed of a car in the passenger seat while blindfolded? So you're sitting in the passenger seat, you're blindfolded, your friend's driving the car. Can you distinguish between, oh, it feels like this car is going about 45 miles an hour? Is that a thing? You feel that? Yeah. Feels like this car is going about 60 miles an hour right now. Okay. Are you on a giant spinning planet right now, going on almost 1,000 miles an hour straight to the east? Yeah. Can you feel that? What can you feel something in a car? Huh. What do you feel, and how could you quantify that? Fancy words. You catch a dropped ruler. So I'll have you guys do this in a few weeks. You're gonna pair up. Your friend drops a ruler. You catch it as fast as you can. Right now, do you think there's a little bit of delay between what's happening in the outside world and your brain being able to make sense of it? Between me talking and your brain perceiving, interpreting what I'm saying? Okay. Right. So your friend drops a ruler. There's gonna be a little bit of a delay before you say, "Oh, I gotta catch that." You catch it. Okay. In the meantime, that ruler has fallen so far. It's really easy to grab the number off the rulers. Okay, fell 19 centimeters. That's easy. Okay. How does that correspond to how much time the ruler's fallen for? Hence, what is your reaction time? Right. And is that a linear relationship, or is it something different? For example, suppose you catch it at 19. Well, let's change the numbers a little bit. Let's do 10 versus 20 centimeters, right? If the roller falls 10 versus 20 centimeters, now that's definitely twice as far, but is that twice the time? Or is that maybe some different factor of time? And what would that equation be? Right? How could that relate to other things? Let's go back to you're driving a car. A deer steps out in front of you. There's going to be some amount of time before you realize, oh, you better slam on the brake. Right? So that takes time, and it takes even more time to actually brake the car to stop. There's also projectiles are part of kinematic motion. This is a lab I'll have you guys do in a few weeks. We'll take some launchers and take some little bouncy balls. We'll go out to this balcony. We'll start blasting the bouncy balls off the balcony. Horizontally up. So we'll aim it horizontal, right? Now, if there was no gravity, it would just keep going in a straight line. But you guys know on Earth, gravity is going to bend down. You think it'll bend down? Look about that shape right there, right? Oh, speaking of that shape, guys, what shape is that right there?
Parabola.
That is a parabola. Yeah, turns out it's a parabola. So if you learn about parabolas and now, you'll see them all over the place in physics pretty soon. What if you take a meter stick, you walk up the stairs, and you measure, okay, I know how high this cliff is right here. It's so many meter sticks tall. Right? You spot where the ball lands. You take either a meter stick or a trundle wheel and measure how far out does that ball land. Right? Is there enough information there that you can back calculate how fast was that launcher blasting the ball? Do you guys think there is? Can you figure that out? True. Yeah. If you change the angle, would it change where the ball's landing? Yeah. So is it really important that maybe you, for this particular setup, maybe aim it straight horizontal like this, straight horizontal? That would definitely matter too, wouldn't it? Because if you change the angle, I bet that would make it more complicated. Yeah. But I bet you could solve it. Maybe some trigonometry, some sine, cosine, you do. All right. How about this? What if you took this whole system to Mars? You take the exact same launcher to a cliff of the exact same height on Mars, where there's really weak gravity, not as much gravity, right? Where do you think the ball lands on Mars? Do you think it lands like closer to the cliff or like way out here? Okay. So something to do with gravity. I bet gravity field is part of being able to figure this out. Like how fast is the blast speed? But you have to know the gravity field of the planet that you're on, right? Okay, more projectile. Let's say you're in a ball throwing contest with your friends. They say, who can throw the ball the furthest? Well, you can only throw as fast as you can throw. So can't really do much about that, right? What you can change is the angle, right? So I know if I throw it straight horizontal, probably doesn't go too far, hits the ground pretty fast, right? if I change this angle, well, if I go too far, what if I throw it straight up, straight vertical, like 90 degrees to the horizontal? Yeah, it comes straight back down, lands where it started, didn't really go anywhere. In terms of displacement, I'd say the displacement is zero, right? Right. So if I want to maximize this horizontal distance here, this horizontal displacement, wonder what angle that would be. What would be the math that could back that up? Hey. Oh, oh yeah, 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 got that's right here. All right. All these red banners, are related to kinematic motion. So there's some linear motion, like I see cars driving here, constant velocity going to stop. I see, okay, here's reaction time, dropping something, balls off cliffs. Right? I see some equations here. I was trying to give you guys some variables and units on a lot of these too. I see some projectiles here, projectiles. Right? I see some graphs. Right? All those. You guys ever been in an elevator? Elevator doors closed. The elevator starts to move. Now, when it starts to move, you can definitely feel that, right? You feel, oh, I feel a change in motion. Feel that, right? Now, what about when the elevator is in the main part of its motion? It's just coasting. It's just going, going, going. Does it feel inside the elevator exactly like it does just sitting in your desk right now? I think it does, right? But what about when it comes to a stop? When it comes to a stop, can you feel that? You feel come to a stop, okay? And maybe it doesn't matter which way it goes. Like if you're going up to a destination floor, if you're going down to a destination floor, starting moving, it's continually moving, it's coming to a stop, right? I bet you could quantify all that motion, or what could help you quantify it is if you brought a bathroom scale along with you, right? So, okay, what is my weight? Just like standing at rest. Okay, now what is this needle pointing to? Say like it various parts of the motion. And what could that tell me about the motion of this elevator? Okay, so if you're looking for that down the line, throw some numbers at you guys. Ooh, look at this bridge right here. You're engineering a truss bridge. Now, there's a form of a truss bridge. It looks like a combination of a truss and an arch, right? Can you determine the tension or compression in any part of that bridge? Like this column right here, or maybe like this beam right here. Like what's the tension? What's the compression? That might help you engineer the bridge in a number of ways. Suppose you're in a bidding war with another company. So there's some local county. The county wants to build a bridge somewhere. Right? They say we want these specifications. It has to be able to carry this many cars, and it has to be this long to cover this river. Right? Right. And there's like 3 or 4 different companies that put in bids. Right. Well, you're going to get the contract usually in the American system if you have the least cost. That's normally what the government's looking for. Who can do it for the least cost? Right. Well, do you want to over engineer this bridge, make some of these like twice as thick as they need to be? Well, that would be extra cost, if it doesn't have to be. So from an engineering point of view, you want to make this sort of like equally strong, or if you like equally weak everywhere, right? So, but you have to be able to calculate what's the tension or compression in any part of that bridge, right? Then you have to know the strength of any materials. Say, okay, well, if I'm working with steel, it has this particular strength. I need to meet this specification. I know how much steel to use. Right? How about concrete? Guys, concrete, you can build skyscrapers out of concrete, huge compressive strength. Right? How about tensile strength? What if you pull on concrete? Does it pop apart pretty easy? Yeah, it has hardly any tensile strength. So if there's some part of this that's in tension, I bet you do not want to use concrete. You want to use steel? Okay. There was a whole college class I took that was just answering questions like this. It was called statics. It's part of an engineering course. So yeah, you do civil engineering one day. Yeah, you see a ton of questions like that. This is a fun one. I hope you guys do this as part of a lab one day. If you know how much friction there is between two surfaces, how can you predict the tilt angle of a desk where the object slides off, or the reverse question? But let's do the reverse. Okay. What if I take some object, I stack it on your desk, I start tilting the desk. Now for the first 3, 4, 5, 6, 7 degrees, you think the object is kind of stuck to the surface because there's friction. Right? Right. But at some point it's going to break that friction and slide off. Right? And I bet there's some relationship there. Just think intuitively between, let's say it breaks at like 12 degrees. That could tell you something about the friction between those two surfaces. And what if you changed out the materials? What if you put down some wax paper, which is real slick, almost no friction, wax paper? You think that maybe a really shallow angle will start slipping? Right? What if you put down sandpaper? Do you think you can do like a pretty steep angle before it starts slipping? Right? Also got, back in the 1970s, there were a couple of spacecraft that were sent off into space. They captured a lot of our pictures of like those gas giants that like fly by Jupiter, Saturn, right? Voyager 1, Voyager 2. And it's still going to this day. Like at the edge of our solar system, it's still going. Right? Still going, still going. How much fuel does it need to keep going? How much fuel does the Earth need to keep going around the sun? Huh. Huh. Yeah, right. Well, what's keeping it going? What's the longest drinking straw that could ever work on Earth? Or how do drinking straws even work? Suppose you were up on the moon. Guys, does the moon have an atmosphere?
Not really.
No, no, yeah, not really, no. Okay, so we'll call it a vacuum, right? Would a straw work in the vacuum of space? No, right? The moon has a little bit of gravity, so maybe you could hold water in a cup. That'd be okay, right? But I don't think a drinking straw would, right? So what is the principle here? Oh, maybe some kind of well, okay. You guys think about that, right? Okay. See, and if we're in some see finite pressure in this atmosphere, what does that have to do with the limit of like how long a straw could work, right? Back a couple hundred years ago, there were towns say on top of a hill, and there's this lake below. They needed to start pumping up the water. And they realized, ooh, there's only so far we can actually pump up the water for it. We can't pump it up above a certain level. All right, what is that level? And what does that have to do with, say, the atmosphere or the physics that are involved? Right? Which force is greater? The Earth pulling on the moon pulling on the Earth? Does the Earth pull on the moon? Does it something to do with it keeping it in orbit? Does the moon pull on the Earth? Yeah. So I mean, we got tides and stuff, right? Huh. But should have shown you guys that. Right. There's the Earth and the moon to scale. So if you were like out by Jupiter and telescoped in on Earth Moon system, kind of what it would look like. Right? What would happen to your weight if you started to tunnel down? And where do you think you would weigh the most? So you pull that bathroom scale from that guy in the elevator. You stand on that on the surface. Okay, so I weigh so much at the surface. Okay? Interestingly, all of us spend all our lives just on the surface. So what if you started to tunnel down? Let's ignore that it's all molten down there. What if you did journey to the center of the Earth? You somehow get all the way to the core. Right. And what about all along the way? So you measure your weight here, and then here you dig a little more, and keep digging, and keep weighing yourself. And what if you take off in a rocket and get further away from the Earth, or let's say a really tall building? Is that my next slide? Yeah, that is my next slide. Okay. Guys, what building is this right here? Aha, Burj Khalifa. It's over in Dubai, the tallest building in the world. I think it's not even a kilometer tall, but just to give you guys a picture of a really tall building. Right? How about you guys ever seen satellites go overhead? Satellites, right? Yes. Sometimes here in Florida, I'll see one go over. It looks like a little tiny dot with a little tiny star, and you'll see it like coasting across the sky in a straight line. Uh, by the way, if you're ever out west where there's hardly any light pollution, you see them all over the place. But here in Florida in the suburbs, like so much light pollution. See one here and there. Right? But anyway, International Space Station. It's about that number there, about 400 kilometers up from the surface. 400 kilometers. Right. So again, that Burj Khalifa is not even 1 kilometer. So times hundreds, whatever. Okay. So they're flying around there. Now, if you were inside the International Space Station, going around the Earth, what does it feel like in there? How much does it feel like you weigh? Yeah, you have an apparent weight of like 0. You feel weightless, kind of like you're out in space, right? Okay, so that's interesting. What if there was a building that was so tall, you just make believe, that it was 400 kilometers tall? So you could go up to the top floor, you could look out the window, and you could watch the International Space Station fly by, right? Where all those astronauts are just floating around, feel weightless. Right? Okay. How much would you weigh at the top floor of a 400 kilometer tall building? Okay. I will spoil this one a little bit just to get you guys thinking. Turns out that you would have about 90% of your weight that you do here on the surface. So if you weigh 100 pounds down here on the surface, you would weigh about 90 pounds at the top of that tower. So you weigh 90 pounds, okay, I lost a little weight, but barely tell the difference. Look out the window, you see those astronauts floating around. What's going on there? Okay. Got some orange banners, got Newton's laws and forces. Got more of those. I think some of these are a little bit out of order. Oops, sorry. We'll just keep going though. Okay. How about this guy here? Got fun bus. What angle would you bank a road going around a curve so that drivers could make the turn even when the road is iced over? See, a lot of these tight turns, they do bank the road. You guys experience this? You guys probably just got your driver's licenses, right? You guys driving around? Maybe the first time you leave the interstate, you're going for like 70 miles an hour. So, you got to slow down in a hurry. You're taking an off ramp and it's really tight curve. It's usually banked, right? And you can kind of feel it too. It's like, well, if I was going too fast or if they didn't bank this road very much, it'd be kind of easy to just like fly off, right? Like that'd be bad, right? So you gotta slow down, roads bank, that helps you out, right? You guys think the tighter the curve, like the radius of curvature, right? Maybe the more you should probably bank the road, right? What if the road was iced over? What if you were up north and the road is iced over? So you don't even have hardly any friction to help you out, right? Do you think you could calculate the angle from the horizontal? You'd have to bank the road so the cars could make the turn even without friction. Ooh, fun times here. Right? Look at this guy going through a vertical loop in this roller coaster. How fast does a roller coaster cart have to go through a vertical loop to stay on the track? Or regular class is saying, well, yeah, the safety feature. Right? What if this guy forgot to wear a seatbelt? Forgot to wear a seatbelt. Right? And yeah, so I mean, if this wasn't moving at all, if it came to a stop there, this guy's not wearing a seatbelt. What happens next?
Oh.
So he gets one more fun ride in his life. Right. But what if he wants to ride many more fun rides in his life? Do you think there's some minimum speed to get around here? Huh. Do you think that might have something to do with the radius of curvature of, what if I hold a circle flush to this part? You see a circle could fit flush right there. Maybe some minimum speed. Do you guys think it might have something to do with also Earth's gravity field might be a factor? Like if this was on the moon, do you think it'd be easier to get that to go through a loop on the moon where there's not as much gravity?
Yeah.
Right? In fact, I know in deep space, you could have like almost no speed at all, and you just would never fall out of the cart. So yeah, I think that would be a factor too. What does that equation look like? How fast does satellite have to go to stay in orbit? Yeah, okay, I do need, these are a little out of order. Oops, sorry. So we're back to satellites again. How fast does our rocket have to go to cut off its engines and coast all the way to the moon? Right. So the last slide, we were looking at something called orbital speed, like International Space Station. This one's something called escape speed, right? So the rocket gets going, of course, it's like blasting right there, big old fireball near the surface of Earth. It gets further and further. The further it gets away, I think Earth's gravity is going to get weaker. But it's not a sharp cutoff, though. It's a gradual decrease. It shows up a lot in physics, right? But at some point, the rocket's going fast enough, and it's maybe far away enough, cut off its engines, and even though it's not blasting the engines anymore because they're off, right? Just keep going, keep going. Called escape speed. What is that? How would you find that? What's the physics principles going on there? Okay, so we got all these purple banners and gold banners. These are related to rotational motion, circular motion. There's reasons for different colors, but whatever, kind of together a little bit. Right? I like those. Yeah, got universal gravitation. Actually, you know what? This escape speed one, it did changes to a green banner for the energy section because this is actually an energy. Yeah, so a little mistake there, but it's out in the future. So we got gravitation going on. Here's an energy question. Here's a real classic right here. Real classic. What's the relationship between car speed and braking distance? Hint, it's not a linear relationship. Spoil it a little bit, just get you guys thinking, well, what would it be then? Right, here's what I mean by that. Suppose you're in a car, you're driving, let's say you're going 30 miles an hour. I'm just going to use American units today, but in the future, might use metric like meters per second. Let's say you're going 30 miles an hour. And there's a car right next to you. Let's say it's going 60 miles an hour, right? And right as it's starting to pass, right, maybe a third person off the side is watching both those cars up in a helicopter, right? 30 miles an hour, 60 miles an hour. And both cars slam on the brakes. Go to a stop. Okay? Now, one car was going twice as fast as the other. Do you guys think they take the same amount of road to come to a stop? Which car do you think takes more road to come to a stop? The faster one. Yeah, true. Right. Now, I said it was going twice as fast, right? 30, 60 miles an hour, twice as fast. Right? Does it take twice as much road to come to a stop? No. Yeah, it turns out the answer is no. And that's exactly what this hint is right here. Hint, not a linear relationship. So twice as fast turns out is not twice as far braking to a stop. So what would it be? Well, hang tight, because that would be good to know if you're driving a car, but good time. Right? Can you amplify your strength? That's to say you get a mechanical advantage with the pulley system, which is one example of, it's called a simple machine. Over in class, you guys see this green trellis here? Got all these pulleys. That's a fancier one. And then this one in the picture here is an old one I have. Right, but yeah, you can amplify your strength. You can see it on the screen here. You can also see it over there in real life. Right? Both cases, I have a 1 kilogram mass right here, which weighs approximately 10 newtons. It's like 9.8 newtons. I'll call it 10 newtons of weight, like gravity force pulling it down. Right? But this spring scale is reads a much smaller value. It's closer to, well, on this picture, closer to 2 newtons, and that one over there, which is even better, is even less than that. Okay. And look at this little tiny weight. This little tiny weight can lift this really heavy weight. Huh, look at that. So suppose you were like real weakling, right? I can only lift 2 newtons. I can only lift 2 newtons. Right? But if you have one of these, have this pulley system, now you can lift up to 10 newtons. Now you're 5 times as strong. Ooh, 5 times as strong. I'll have you guys construct some of those one day, be one of your labs. Right? Can water flow uphill? So do you guys ever see balls rolling uphill, water flowing uphill? Not normally, right? And why not? And if there are some exceptions, what would be the case of those exceptions that would still be consistent with the laws of physics? Something called a hydraulic jump here, so that's fine. Right? How about perpetual motion machines? If you ever look at the diagrams that say Leonardo da Vinci was trying to invent some of these, and a bunch of inventors over the years, no one was ever able to make one of these. So it brings back to say the energy that we're using in this classroom right now, the lights, the air conditioning, and so on. It's all connected to the electric grid, and on the opposite side of the electric grid, there's various power plants, right? Maybe like burning coal, burning natural gas. There's some uranium. There's boiling water that's turning a turbine, pushing a wire past a magnet. Right? That's transferring energy onto the grid, right? Well, if you had something like this, going to that picture back on the slide there, is there any way you could set up a wheel with a bunch of ball bearings and just have it continually move and then set that up to a turbine and then you can get energy for free? Wouldn't have to use coal. And no one's ever been able to make one. Would it be okay? Well, looks like the implication here is no, that can never exist. But why would that be? Yeah, and how does that help you maybe solve a whole host of other physics puzzles? So all these green banners are related to something called energy, conservation of energy, work. Right? So there's these different forms energy can take. A bunch of classic examples here. Again, any classic puzzle that shows up in physics, especially AP, turn it to a poster for you guys, or some simplified form of it. Right. Can you determine the firing speed of a bullet by firing the bullet into a pendulum? I don't have a picture for that. Well, okay, someone called it a ballistic pendulum. I'll tell you guys what it is. Use your imaginations now. So say it's the year 1880. You have the new revolver. Fire some bullets. I wonder how fast can this gun fire? So what they would do, because how do you figure out in 1880, right? Is you measure the mass of your bullet. You measure the mass of a block, big old wooden block. You hang the block on a pendulum and you measure the length. Right? Then you fire the bullet into the block and see how high up does it swing. Now, if you know that, if you know the mass of the bullet, mass of the block, and how high it swings up to, and also Earth gravity, there is enough information there. We can back calculate what was the firing speed of the bullet. Now, that's a collisions type question. Anything that's a collision question is going to be, well, this unit here, momentum. I forget if this unit number is the same. It might not be unit 5 anymore, but yeah, momentum, collisions. Can a bouncy ball return higher than it was dropped? Suppose you get the world's bounciest bouncy ball and you drop it from 1 meter high. How high can it drop? Can it rebound? Okay. What if you get a half deflated tennis ball? Right. What if you get a like a blob of clay stick to the floor? Okay. Hey, I wonder, is there some way you can quantify how bouncy is something? And what would that be? And how could you describe that numerically? What equations could that fit into? Once a billiard ball has been set into motion, is everything that results determinable? So you strike the cue ball, all the other balls are in place, you know their masses, you know how bouncy they are, right? Is everything, after you set the first ball into play, that's going to happen in the next 5 to 10 seconds, is that all determined at that point? Yeah. Can you calculate that all? If you know some trigonometry, you know some collision physics? Yeah, probably know that. And if you play billiards, maybe you can figure this out intuitively too, but we can do the math. Okay. Some crazy implications of this too, because if this is determinable, how much of the world is determinable? Is your brain made out of matter? Is where do your thoughts come from? Which thoughts do you act on? Is that your choice? Is that predetermined? That's a big question too. All these blue banners. Yeah, I do have some updates. So there are some new ones that I also made for you guys too, but small version. All these blue banners got collision physics, momentum. Right? Ooh, in a few months, we're about to have the Winter Olympics are coming up pretty soon. Winter Olympics. You guys ever watch figure skaters? Say they hold their hands out. They go into a spinning motion, hold their hands in, and start speed up spinning. You guys ever see that? Oh, yeah.
Is each page for a different unit?
Pretty much, yeah. Yeah, so yes. So you guys are seeing the colors of these banners changing. Right. So all the blue ones are momentum and collisions. All the green ones are energy. Yeah. Yeah. So every color change is a new section. Pretty much, yeah. Okay. Uh, yeah, so what's the physics going on there? How much effort does it take to pull your arms in while you're rotating like that? That takes some work to do that. Okay. Ooh, equilibrium rule. I saw this picture from Paul Hewitt. You guys might remember on their I uploaded some of his videos already to Google Classroom. Right, go head start, right? But one thing got him interested in physics was the scaffold question. So he was a sign painter. He and his friend would be painting these signs in Florida, walking on a scaffold that was held up by these two ropes, right? And he said, "Hey, walk over towards me." So he's here, his friend's walking towards him. He's plucking this rope. It's going boing, 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 boing. His friend's walking toward him. So go back the other way. Walk towards your side. Boing, 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 boing. And if the tension in this rope is changing, how do you think the tension in this rope is changing? Huh? Okay. And what does that have to do with the weights of either of these guys or both of them, and the weight of the scaffold, and where those guys are positioned? Because it looks like as they're walking around, the tensions are changing. Huh? What's that relationship? Huh? How about hurricanes? Looks like we already got a hurricane forming. Looks like it's gonna miss us, by the way. But guys, any hurricane that comes over Florida, do you guys notice it always rotates which direction? Counterclockwise. Yeah, yeah. Why do hurricanes form at all? Why do they always rotate counterclockwise? At least over Florida, right? Um, Here, I'll give you guys a hint. If you go to the eye right here, go to the eye. Is that a high or a low pressure? Low, yeah, low pressure, low pressure. Yeah, so low pressure. Now, if you have a low pressure, would that be vacuuming in all the air mass around it? Yeah, because low pressure is vacuuming in, right? Now, it turns out if you are on a spinning ball, so like a rotating sphere like Earth, right? When you change latitude, there's a discrepancy between it's called linear velocity and angular velocity. So that's something called the Coriolis effect. Yeah, you can get these hurricane systems, right? What if you go to Australia? What if there's a cyclone that hits Australia? Guess which way it rotates? Yeah, the other way. Okay. Do that later. You guys ever done that? How are we doing on time here? Got about 8 minutes. Okay, yeah, thanks. You guys ever try to balance somewhere? Try to balance, right? And you guys do it just like they are in the picture, like hold your hands out like this. Does that help you balance? Help you balance? Yeah, or in one case they're using a pole. Look at that person using a big old pole right there, help balance on that high wire, right? But what are you changing? Are you changing your weight? No? Are you changing your Does your center of gravity really big? Huh. I think it kind of averages out to pretty much the same point, pretty much. Right? Huh. What are you changing then? And what's the physics of why that would help you balance? Even though you probably figure this out intuitively, right? Right? Here, give you guys another example, the same idea. You guys ever try to balance a pin on your finger? Can you do that? Yeah, the answer is no, but nearly impossible. Right? But if I give you guys this meter stick one day, you guys think you can balance a meter stick on your fingers? Look at that. Yeah, pull it out here. So not in front of the camera, but yeah. Look at that. Pull it up all day. Look at that. Huh. Yeah, this is easy. Right. This is pretty much impossible. Huh. What's the difference there? Well, I'm showing you guys some tools. Here's 1 meter, by the way. Meter stick, about 3.28 feet about. Right. Here's 1 kilogram. Pass that around someday. Yeah. So we're working towards all that. We're getting there. All right. Here I'm gonna pass these around. So you guys get your hands on these. What is 1 kilogram? What is 1 meter stick? You might do that. You probably forget, but all right. Forget I did that. So 1 kilogram, 1 meter stick. All right. Those are the base units for mass and length, by the way. Measure more. All right. Ooh, let's have a roll race. What if I have a solid bowling ball? I have a basketball. Now, guys, a basketball, do you think its mass is pretty much on the surface for the most part?
Yeah.
Yeah, right. I got the solid cylinder. I have a ring. Right. And I let all those roll down the hill. Let's say there's some friction just to induce the rolling. So they all start rolling. Okay? Do you guys think they're going to tie, or do you think somebody's going to win that race? Yeah, somebody's going to win. There's going to be a ranking. Somebody's first, second, third, and fourth. Right. Give you guys a little hint. It turns out that it has nothing to do with the exact mass or radial sizes of any of those rolling objects. it has everything more to do with how that mass is distributed. So the fact that the bowling ball is solid, the fact that the basketball is like a spherical shell, and so on, right? How is mass distributed? Yeah, somebody's going to win that race. It's going to be ranking. Okay. So all these purple banners are related to rotational dynamics, which AP as of last year, oh, I think my screen's frozen, divvied into 2 units. All right, come back screen. Oh, okay, we're back. Okay. Pressure at the bottom of a pool. You guys ever dive down to the water? Deeper you go, you guys feel that pressure increasing? Right? Now, it turns out that depth is not the only factor for pressure. There's some other factors too, like if the water is in motion. Well, this speed and pressure of water change through a pipe system through various diameter pipes. What if the diameter is changing? What if you go from a big pipe to a small pipe? Right? Could you imagine if you're a fish swimming around inside the water in the pipe system? Fish swimming around? Okay. So you go from a big pipe to a small pipe. Now, there's a conservation of flow. So like the flow rate, gallons per minute, conserved. But what do you think happens to the speed of the water? Huh. Right. And what do you think happens to the pressure in the water? Again, if you're that fish, you feel the pressure change. Huh. What happens and why? How about this guy? He's using a hydraulic lift. So maybe with a small input force, he can lift a really heavy car. Oh, kind of like that pulley system over there. Get a mechanical advantage, right? Mechanical advantage. That's all these orange banners here. All these orange banners related to fluid dynamics. Well, most of them. I got some engineering down here. Just trying to fill the space there. All right. But, yeah, fluid dynamics today. All right. And then the last unit by AP's book anyway is oscillation. So here's an oscillation question. What if I have a spring, it's just hanging vertical, and I start to hook a lab weight to it, right? And then I drop the lab weight, let it go. And it overshoots the equilibrium, it goes to some maximum stretch, and then oscillates back and forth for a while. Hey, how much time does it take to oscillate back and forth? Do you think that has to do with how stiff the spring is? Do you think that has to do with how much mass is the lab weight? Do you think it might have something to do with Earth's gravity field? Or if I took that to the moon, could it possibly oscillate the same time period? Right, time will tell. Right? And then when this eventually comes to a stop, after a couple minutes, right, how does this equilibrium stretch compare to this maximum stretch? And what would the formulas be that could predict that very well? Okay, so that'll be a lab one day. Right? So all these gold banners, back to oscillation. There's some wave stuff on here. Right? Now, AP used to ask about waves a few years ago. They dropped that, but kept the oscillation. Right? Now, there's a bunch of little topics that I teach my other physics class. I might take a day or two here or there to fill you guys in. Right? So like waves. You guys ever hear a car go by on the road? Hear that pitch shift? Right? If you're inside the car, you don't hear the pitch shift. If you're out on the sidewalk, you do. Right? What is that called? That's called the what effect? Doppler effect. Right? Could that tell you something about how fast the car is going? Right? Or what about this ice cream truck? Right? But electric circuits. Again, about 6 or so years ago, AP used to ask about this. They dropped it, but I will take a good few days to do some circuits with you guys because it's good for you guys to know. How does current flow throughout a circuit? What does resistors in parallel or series mean? How does that relate to traffic flow and water flow? How can you turn this into electricity on the grid? How do you go from coal to electricity, right? Right. So that just involves running a wire past a magnet. I might have you guys build a motor one day, although it's not going to show up in the AP exam, but good enough. Class. All right. There's also optics. You guys ever put a pencil in water? It looks like it's bent, or your friend steps in the water, like, hey, what happened to your legs, man? It's like, oh, wait, no, you're good. It's just optical, right? Called Snell's law. Got some engineering going on. Got some thermo. Relativity. Turns out the GPS in your phones would not actually work without Einstein physics from 1905. Physics got a huge facelift. Quantum mechanics. Pretty exciting fun. All right. Guys, here I know we got about a minute left here. So here in the last minute, one of the pages I gave you guys, it's in that plastic page protector. I have a couple of pages here. You guys see these 2 pages I'm toggling between? Just 2 pages there. I give you guys a list of variables and units. What does this variable mean? What unit would you measure this in? And maybe a little equation. So for example, you guys see this L for length? I'm going to measure that in. What do you think M stands for here? Meters. Length could be meters. That's okay, right? Right. How about, here's a different M. Guys, what is M? Not as a unit, but as a variable. M could stand for what? Mass. And guess how we're going to measure that in this class? We're going to measure in, what do you think KG stands for? Kilogram. That's that kilogram that's you guys are passing around right now. 1 kilogram. about 2.2 pounds, by the way. All right. F could stand for force. Measured in, what do you think force is measured in the metric system? Newtons. Good call, newtons. Okay. I need to take a day to tell you guys about measurement, but anyway, take a look at this though. Next few days, variables, units, we're going to be using all those over the course of the year. But I am out of time, so we're gonna hang that up right there. You guys ready for lights? Lights, lights, lights. All right, you guys, have a good lunch. Have a good day. I will see you tomorrow. We will construct a Geneva Drive. Oh yeah, Geneva Drive.
Hey,